Let's take a look at alkylation of enolates. So if we take a look at this ketone we have here, so we have two methyl cyclohexanones, so you can obviously see that there's 3 alpha protons in this molecule. So there's one here next to the methyl group, and then we have 2 over here. So if we treat this with a strong base so that we do an irreversible deprotonation to form an enolate, which proton are we going to remove? Are we going to remove the red proton, the one adjacent to the methyl group, or are we going to remove the blue ones that are less hindered? Well, it depends on the base and the temperature that we use. So in chapter 22, there's 2 kinds of conditions that we look at for alkylating. So the first condition that we're going to talk about is removing one of the blue protons. And to remove one of the blue protons, since these are the less hindered protons, these are less hindered because they don't have that methyl group in the way we extract those is by using LDA, so lithium diisopropylamide, and we're going to use a very low temperature. So we're going to keep things cold at minus 78 degrees. And you can imagine what happens after you remove one of these protons is that, and I'll just get rid of that, so you end up forming an enolate. Okay, so you form an enolate that looks like this. So you formed the enolate on this side of the molecule. And so what you can imagine is if you treat this with an alkyl halide, so I'll just draw Rx as a generic alkyl halide, that you'll get movement of electrons to come attack the carbon, and then you'll lose a halogen, and then what you will get is this product. So let me just draw this out where you have your R group here, you have your methyl group on the other side, and your ketone is intact. So this, when you're using LDA, and I'll put this as your second step, is adding the alkyl halide. So when you add LDA, you're doing this at cold temperatures. So not only are you doing it at cold temperatures, but LDA, if you remember the structure of lithium diisopropylamide, it's a big base. It's got 2 isopropyl groups. So if we draw out the structure of LDA, it's got these 2 big isopropyl groups that are sticking in the way. And that makes it more difficult for it to extract the proton next to the methyl group. So it's big, it's hindered. So it goes for the protons that are easier to get to because there's less crowding them. There's less steric interaction there. Excuse me. So when we use LDA in a cold temperature, this is the regioisomer that we get. Now let me just grab this, cut this out of here. And we call this product, the kinetic product. The kinetic product. Oops. Kinetic product. And what's important about the kinetic product is that it proceeds through the less stable enol. Because if you imagine if we had the double bond over here on the other side next to the methyl group, it would be a more stable double bond intermediate. So the other set of conditions we're going to look at use a much smaller base. So they use, step 1 will be to treat the molecule with sodium hydride at 25 degrees Celsius. So we're going to be at warmer temperature, and we're using a much smaller base. If you imagine sodium hydride, you can actually write it out, as an ionic species. So this is the base that's actually going to remove this proton. And as you can see, it's a much smaller base than LDA. Therefore, it can get in there and grab that proton adjacent to the methyl group, and then this is what you will form as your enolate. So you put your negative charge on your oxygen here, and you draw the double bond. And this time, you will get the more substituted. Enolate. So your double bond, you can see, I'll circle that in green. You get the more substituted double bond this time because it's got a methyl group on it. So if you treat that again with an alkyl halide, let me get my red pen back here. So if step 2 is to treat that with an alkyl halide, as you can imagine, your electrons will come down here and will attack your alkyl halide. And what you will get as a product, in this case, is you will have your methyl group and you will have your R group. And this product, we call this the thermodynamic product. Thermodynamic product. So you can see that by treating an unsymmetrical ketone, so it's an unsymmetrical ketone because on this side we have a methyl group and on this side we have 2 protons, so it is unsymmetrical. And when we treat an unsymmetrical ketone with a base, we can choose our base, and if we use LDA at a low temperature, minus 78, we get the kinetic product where we alkylate on the less hindered side of the molecule. The less hindered side of the molecule, so I'll put that here. And when we choose sodium hydride as a base, hydride is a much smaller base than LDA, and it is going to abstract the proton that is next to the methyl group to generate a more stable enolate, because the double bond is going to be more substituted. And then from here, we get what's called the thermodynamic product. So just to reiterate, when you want to do the alkylation of an enolate, the choice of base and temperature is how you control whether you get the kinetic or the thermodynamic product.